Hello everyone. In this session we will discuss about box girders, steel box girders with concrete slab on top. We will learn how to model them as 3D, mesh them with finite element plates, apply the loads, do the analysis, and finally design and get the stress results for the box girder beams. I will model a box girder bridge as 3D. So firstly I will model the first beam, and afterwards we can generate the bridge as a 3D model. So like always, to start the project I click the new project here, go to the project configuration. Firstly, you can add the name or number of the project here, and here I'm going to define this project, the analysis, as nonlinear analysis, and I'm gonna leave these default values as R. And in the composite beam tab, because the project is a composite beam, box girder with concrete slab on top, so I will define construction stages here. I will define stage 1, stage 2, also stage 6 and 7 for this project. The other values are okay here, the default ones. So click OK. In the next step, I will model the project. So firstly, we will model the first beam here, and afterwards we can generate the beam to have the full complete 3D bridge. And the bridge will have 4 box girders to cover this span. So I am in the node mode, Control H. I will add 2 nodes. For the first girder, it's starting from 0 coordinates, and I'm going to define these lengths of 42 meters in the Z direction. Okay. So if I zoom, I will see these nodes here. After that, I can add the first girder. So we go to member, add, and I will put my girder here. So all of the default values, I'm going to keep them here. For this section, I will use an MTO1 box girder section. As you see here. Okay. For the material, let's use 4350. For the dead load, we will not define it yet because it is a stage construction. And also we will activate design criteria. And because the project is composite, so here we apply composite beam. In the next tab, I will define the effective stage of the beam as stage 1. So here I've defined my section to be activated in stage 1. And here these are the properties for the member. And for the dead load, as you see, I've defined it as it's empty. And the dead load of the box girder is different from the I section that I've discussed it with you in recent sessions, because the box girder we are going to mesh it with finite element plates, so the dead load will be applied using those finite element plates and not here. I click OK, and if I bring up the 3D view, you will see the box girder is already defined here. The geometry, I don't have the slab yet, so the next step will be defining the slab, and I'm going to define the slab right now. So we go to structure, slabs, and you can add a row here to define the slab. So I will name it as composite slab. Concrete material, I will use concrete 030. We don't have a steel deck. And the thickness is 250 millimeters. For the reinforcement, at top I'm going to use 15 m's with spacing of 300. Distance the top I will define it as 270. And for the reinforcing bars at the top, at the bottom, it will be 15 m again with 300, and distance will be 270. The material I will use 400. And if you want to check out this slab visually, you can always right click on one of these cells, click detail, and you will have the definitions here, and you can even modify them here if you want. Okay. So I defined the slab. Right now we can define our composite beam. So I go to selection mode, member mode, double click, and composite beam. So here we have that slab available. I'm going to select this. For the studs, 22 millimeters, and for the B I will use 5 meters, 5.2 meters. Same for the actual. I will define 6 studs in a row. And here, because it's a composite project, I will remove this and check mark these 3. I want to have the composite properties and also include the reinforcement for both bendings, minus and plus. And also we will activate the slab or composite section from stage 6. Click OK. And as you see, I have this slab placed on top of the steel section. In this bridge, I will have steel frame diaphragms for the bridge, and I will define the value of 7 meters between the diaphragms. So to add the diaphragm framing to the bridge, I will divide this using the ADA's split multi-split tool to have small segments of this girder. Each one has 7 meters length, so it will be 6 subdivisions, split members along with loads. Yes, save the project. And here, as you see, ADA divided the beam to small segments of 7 meters. Okay, and also to have the finer mesh when I am meshing my members or my beam here, I will divide all of these, each one, again for 4 small beams. So select them, and here each one will be divided by 4. Okay. So each 4 of these elements here is a span between my transverse diaphragms. Okay. In the next stage, I'm going to copy and paste this beam transversely along this x-axis to have 4 box girders and form the bridge for this span. So we can select all of the elements here, Control C or copy. It will be X direction and 5.2 meters, the distance between the girders, and Control V. So you will have the second box girder, and also I can continue this, so because they're already, we need to firstly select them again. So here, select the beams, Control C, it will be 5.2, and Control V. Finally, Control C, 5.2, and OK, Control V, paste. So I have my bridge modeled. Here I have all of the 4 box girder beams and the slab on top. And you can always use this option here to graphic quality of display and translucent surfaces, so on, and you will have a better view on the elements and better line of sight. The next stage is the mesh the box girders. Because in ADA we use the steel plate finite element plates to model these box girders, and we will have the stress results and other kind of results available for the designer to check at the final stage. So ADA has a tool to automatically mesh these beams, so I will use that tool here. We need to just select all of the members and tools, members, and we have the mesh command here. So when I click that mesh, as you see, ADA is meshed my beams. So in this view, you see both of them. You see the linear box girder that we already built, and also you can see in green color, you can see the finite element plates that ADA is generated. So we can always hide the previous ones, the linear members. To do that, we use the mask command here. So we firstly select these plates or activate the plate selection mode here. Select the plates and we will mask them. So in this view, you will only see the plates. These are the finite elements plates that ADA generated based on the geometry of your box girders. The top plates are the concrete. These are the flanges of the box girder and the webs here as steel plate girders, finite element plates. And you can also access the properties of these members here. For example, if I double click on this member, as you see here, I have the thickness, the material, and also this is the dead load that will be applied as the self weight of the box girder here. In the next step, I'm going to add the transverse members and diaphragm frame, because right now we have the nodes for the box girder and we just need to define the nodes and the members between these nodes. So I will go to the addition mode and additional members and just click between the nodes here. Let's say I will add a horizontal stiffener here, frame. Okay. I'm going to use the angle 76 by 76 by 11, for example. Same materials. And for these members, I will define their dead load as the self weight. They are not composite, they are standard. And I will need them to be designed by ADA, so I leave the check mark here. Okay, as you see, the L section is here. So to have a middle node on this member here, we can just select it. Go to the selection mode. And using the split tool, I will split it at 2. So I have an extra node here, and the member will be continuous here. So I can add the other transverse members here. So like this, click the first node and the final node. So the defaults here, okay. And this is the other one, and also I'm going to do that for the right part. Okay. I have also another member horizontal here. So as you see, I've defined the part of transverse members inside the box girder. You can always change these members or modify them, and after that we define this for the first girder. We can always use the copy and paste option to copy to other girders. For example, if I want to modify one of the members here or two of them, we need to go to selection, member, and select these with holding control, and after that control H to modify the material or end conditions or other kinds. For example, if you want to change the end conditions to put them just as hinged, here we need to just right click, replace, and define them as hinged in MX and MY. Okay, and if I activate these end conditions here to view those, as you see, all are defined as hinged end conditions. So I'm going to select these members and define their end conditions as hinged as well. Okay, as you see, they are hinged. I'm going to define these two members as T sections. Let's say this one. Okay. And if we want to make these continuous, we need to remove these two hinges here. So double click and change this to one side hinged. Okay, so as you see here, this end is hinged, but in this end it's continuous. I'm going to do the same for the other one. So this one, the first will be continuous. Okay, so this member here is continuous, and the other ones are hinged. So as you see, you can always modify your members here. This is an example. As I already explained in the previous sessions, these are just examples for you to learn how to use the software. And you can always define any kind of member you want. So in the next stage, I will copy and paste these members here on my other girders. So I have the distance already between the girders, it's 5.2 meters. So you need to just select the members, Control C, X direction, and as you see here, because I will use it as minus X, so it will be minus 5.2 meters. Okay, Control V, and as you see here, the members are added here. I will do the same for the other ones, and the final one. Okay. And also, if you want to add some other members here between the girders as diaphragms, you can use the same method. For example, I'm going to add another member here. On this node. Add. So this is the middle node of the flange to the other middle node. So this one will be 2-side hinge. Okay. Another L section down here. Okay. I'm going to use the match properties tool here. So select one of the angles, match properties, and click here. So I have the L. I will divide this member to 2. Okay. And add 2 braces here as well. Okay, match properties. So these are the L sections. Okay, now, like before, we can copy and paste these. So select the members between girders. Control C, -5.2, okay. And Control V. So they're placed here. Also, so as you see, I generated the transverse members here for my box girders. And because we already defined this span or this bridge to have each of these diaphragms in 7 meters, so we can again use the copy and paste tool to generate these along the bridge. So I'm gonna select these frame elements, Control Z, X will be there, X will be 0, and now we are going to generate them in Z directions from each 7 meters. Okay, so this is the second frame as diaphragm, and as you see, ADA is automatically connected the nodes. and I'm going to do this for all of the span. So select, Control C, OK, Control V. And the final span. So this way, as you see, very easily and fast, I have defined my diaphragms. In the next stage, I'm going to show you how to even define some extra L sections here to provide some lateral support for the girders. So to put those members easier, I'm going to hide these, which already defined. So select the plates, selection mode, mask them, OK. And also I'm going to use the side view and select these plate elements for the box girder only and cover the slab part. So again, select, and here, as you see, I'm just going to select the steel part, mask it, and if you see right now, as you see, I have just the finite element plates of steel box girders. I don't have the concrete yet. I mean, I've hidden it. So right now it's easier to put these transverse, extra transverse members to use them as lateral supports. So add mode, member, and I'm going to define those members like braces and KBBL or angle, for example 102, 11. Dead load will be applied and active design and their standard. Okay, this is the first one and the other one. Okay. So as you see, 3D modeling in ADA is very easy. ADA has different kind of tools to generate the geometry, and also if you have a complicated geometry, you can define the members manually. Okay, and the final span. So right now I'm going to show you another feature in ADA. Because these members are braces, I want to define them to work or to take only tension. So you can do that. Firstly, we select these all of the braces here. Go to the properties. And here, as you see, we have an option here, axial FC, and you can define the member as tension compression, tension only, or compression only. So for these members, I want to define them as just tension members. So I'm going to define them like this, okay? And if I double click one of them, as you see, it is a tension only member and it will not transfer or take any kind of compression. This is an option in ADA that you can always use. Okay. Also, I'm going to add same kind of braces here for these members or for the last girder. So as you see here, I have a problem. I wanted this member to be exactly at the middle node. So you can always delete this, or with Control Z or undo, you can remove it and define it again. Tension only, okay. Here. Okay. Modeling these box girders using the finite element plates will help the designer to have better results, accurate and more detailed results. So that's why in ADA we are using the finite element plates. And you can always even make the plates or the finite elements even smaller or have finer mesh. In this project, I'm just going to use the same default mesh that ADA is already generated, but you can always remesh these plate members to have even more accurate results, but your analysis will take a bit longer because of the more degrees of freedom and more nodes that you will have in the model. Okay, so right now I've also placed my transverse members, as you see. Next step is to define the supports for my structure. So I'm gonna put supports under the bottom flange of the box girders. So we need to select the nodes first. Will be this node here. Hold Control, and you will have the second one here. And also I'm going to select those nodes for the other beams. Okay, so as you see here, 8 nodes have been selected. And after that, we can bring up the spreadsheet for nodes by hitting Control H. And as you see here, I'm going to define these as support. Okay, now as you see, these are supports. I will release the moments here and also the reaction along the bridge, or Z action, Z reaction. So right now we go to support mode, select them, Control H. So for the Rx, I want them to be fixed. For the Ry, which is the gravity, it's fixed. Rz, I will release them, so it will be free. And also for the moments, I will release them and they will be simply supported. So as you see, I've used the spreadsheets to do these modifications, but you can also have just click this here, the icon here, properties, and you can bring up the window here and do the modifications via this window. So as you see here, these are my reactions. So I have just gravity here and the X or transverse. For the other side, I will select the nodes again. And node mode, selection, hold Control. Okay, Control H, change the support. Okay, and like you saw before, select supports here, this side, Control H to modify them, and in this side I will have this Z reaction fixed, the others are okay, and the moments I will release them. I want to have a simply supported span. Free. Okay, so as you see here, these are the reactions in this side. Always save the project with this icon. And to have all of the members and other geometry here, you can unmask them. So here you have the unmask. And as you see, I have the full bridge here. In the next stage, we need to define our steel specifications to do the design. So we need to use this option here, specifications, steel. I'm going to add a new one here and name it as S6 box. I'm going to use S6 2014 here. it will be a verification, and the other default values are fine. Okay. And after that, we need to use we need to choose just the members here, all of the members, linear members. Okay. And Control H. In the Style tab here, as you see, we can define our specification here. So replace 6 box as design. Okay. And okay. So I have assigned the style design to my members. So to make the modeling easier here, I want to learn you how to define a selection here, a specific selection for the members in ADA. So for example, let's say I want to define a specific selection just for my beams here, the main beams, and not for the transverse members. So to do that, firstly, we can use or select all of the members here. Control H, bring this window up, and here we can use the ADA's again spreadsheet feature to select just the beams. So as you see here, I can sort this spreadsheet according to sections or whatever properties you have here. I want to sort this spreadsheet by the section shape, and I will just select the sections with box girder MT01. So as you see here, I've selected here, and if I click OK, as you see here, only the sections with box girder MT01 is selected here, and the others are not selected. And I can define a new selection for this. So because they are already selected, we can go to Edit, Select, Create a Selection. So this will be a new selection for me, and I'm going to define it as beams. Okay. So from now on, whenever I want to select those beams, I need to just go to here, Edit, Select, choose a selection, and I will have the beam here, as you see, beams. And these are that you see here, these are other selections that ADA uses for the finite element plates, but our own manual selection will be here, beams. And if I click it here, okay, as you see, ADA just selects the beams, and you can even mask them. And as you see here, these are only the beams. So right now you can modify the beams or work on the beams only. And to unmask them, just click this here. Also, another shortcut that is very helpful in ADA is Control K, that you bring up this selections menu, and you can select your selections here. Okay, so as you see, this is the selection feature in ADA that is very helpful in modeling. So in the next stage, I'm going to select my main beams here, go to their properties here, style design. So I'm going to define these again here, style specifications, and define lateral supports in top of the section. And also I'm going to define stiffeners, let's say from each 1.75 meters. These are the shear stiffeners. And also you have the opportunity to define some longitudinal stiffeners here that for now I'm not using it. So clicking OK. And if I just select one of them, you will see that everything is defined here. So I have the S6 box for design specifications. These are the lateral supports. And I have the stiffeners here already defined. Okay. I'm bringing back the other members. Also, to design these members, the top braces here, we are going to assign them a continuous lateral support. You can again define these, define a selection for these members. Okay, can mask them. And let's define a selection for them. Select, create. So I'm gonna name them as braces, top braces. Okay. And for these members, for steel section, I will define a continuous lateral support for them. And also I'm going to define the calculation of these buckling lengths as 0, because they are not in compression. Okay, so again, if I double click, still, as you see, they are continuously laterally supported, and their K values will be 0, which will not take into account the buckling. Okay. In this part, we will define the load cases for the bridge. So I'm going to use just some simple load cases for just a demonstration. So we have the dead load here. This dead load is the weight of the just steel box girders. I'm going to add another one as cast concrete for slab. So this one we will define it as S6 cast concrete, and this one will be the prefab components. S6 prefab components. I'm going to also add some asphalt as bearing surface. And let's say a barrier load case. As cast concrete. And as you see, the dead load will be automatically calculated here. The others we will apply them manually. So I click OK. One thing that you need to be sure is that if I select all of my finite element plates here and mask them, you need to be sure that for the steel parts or steel box girder, If I click one of those, I have the dead load defined. So it is the dead load coming from steel box girder itself. But for the top part or slab, which is here, as you see, these are the concrete slabs. If I double click, the thickness is okay, is there, the material is there, but we need to remove this. We don't want to apply the slab weight here because it is a stage construction and I want to apply the load in stage 2. If you put it here, it will apply it from stage 1. So one thing that we need to do is you can always go to side view here, just select the concrete slabs, with the restricted view, window, and activate the plates and just select these concrete slab. So mask it. So check it again, and if you check, you will see that it's only the finite element plates representing the concrete slab. So right now all of these are selected. You can just hit Ctrl H, and in their dead load I'm going to put them as nothing or no. Replace. Okay. So right now ADA will not apply any dead load for the concrete, and we will be able to apply it manually and activate the dead load for them starting from stage 2, which is the casting. This is very important. If you don't do that, the ADA will calculate the weight of the slab twice. Okay. So I save the project. Unmask everything. And right now I'm going to apply these load cases manually. So first one will be the cast concrete. So select the mesh, side view, select just the concrete finite element plates, mask them. Okay, and now we can apply the cast concrete here manually. Control H. So I will define it as minus 5.4 kilopascal. Replace minus 5.4 kilopascal, and it will be global direction. So as you see here, ADA has applied loads. To have much faster graphics, I'm going to deactivate this feature here. Okay, so we will be a bit faster. Increasing this, as you see here. I have the weight of slab applied on the finite element plates. So this was for the cast concrete of slab, and for the other load case it will be the asphalt. The asphalt also will be applied on this concrete finite element plates. So we need to just change this asphalt. Control H. Firstly select the members or the plates. Control H. Again, it's a pressure of let's say 2 kilopascal. Minus 2. and global direction. So this is the asphalt. And also I'm going to apply a barrier load. For just demonstration purposes, I will use these elements, the edge ones. This edge and the other edge to apply the barrier load. Replace, and let's say it will be -10. Global. Okay, so as you see here, I've applied my barrier loads here also. So you can add whatever extra loads that you need here. I've just defined 3 of them for simplicity. Next stage is to define the load combinations. So loads, definition. Firstly, we are going to add our construction stages. So let's say stage 1. It will be a construction stage, and it will be activated in the first stage. Stage 2, again construction stage, and here stage 2. We will have stage 6 also, and stage 7. Okay, and after that we will apply the loads and factors here. So for stage 1 we will have just the steel box girder, so it will be just a dead load. For second stage, I'm going to define just the cast concrete or slab. Stage 6, asphalt. And stage 7, let's go with barriers. Okay, so right now if I check my load combinations list here, as you see they are all defined. And now we can go to load generation, load combination generator here. So it will be a 6. And it will be adding here and generate an envelope. So next, these are the load combinations. So we don't have moving loads yet, no, and seismic, no. Next, so these would be the load combinations that ADA wants to generate. Finish. So as you see, ADA generated just 5 of them here. And to have the design for stages here, as I mentioned before, I'm going to copy and paste them here as ultimate, Control C, here Control V. So I will change their name as design. And we will define them as ultimate status to have the design results for these stages. Okay, so right now we have defined our load combinations. We have defined the special load combinations to have the design results for stages. Now we can start the analysis and design of this bridge. So you need to just click this icon here, save the project, yes, and analyze. ADA starts the analyzing here. This analysis may take a bit longer than others because we have finite element plates and much more degrees of freedom. So as you see here, the calculation is complete. Close. Always remember to check the results, load combination summary to see all of the analyses are okay. You don't have any errors. Okay, so analyses are done here. If we want to check for the design results, we can always go to view options, results, activate this option here, design results. Okay, and as you see here, ADA provided the design here for my bridge, and also you have the design for these transverse members. So if I just mask the linear elements, and I can use my selection, beam selection here, so just hit Control K, select the beams, okay, and mask them. So here you will see the design is almost okay for this bridge. Of course, because I don't have any moving loads here or extra dead loads, I have very low design ratios here, but as I told you already, this is just for demonstration. And also to have the results for these transverse members, you can again unmask everything, select the linear members, mask them, and right now I'm going to use the inverse selection. To do that, you need to just select the beams, Ctrl K, main beams, okay, and inverse your selection. To inverse it, you can go to Edit, Select, and Invert Selection, or Ctrl I, and right now you can mask the other transverse members because they are already selected. Mask them, and as you see here, I have the design results for these members. You have the numbers here, design ratios with color counters. So this is the design results. You can also view the moments, share, and others. For example, if you go to design options, I deactivate this, and if we want to check for MX numerical, it's okay. You need to select your load combination here. Let's say for stage 1, and ADA draws here the moment diagram. I'm going to select just the beams, so Ctrl K, beams, okay, mask them, so it is more easier to see the results for MX kilonewton meters, and you can always increase the size of the diagram or increase the size of the font. So this is the MX control options. You can have VY, the shear, and you have other results. Also, you have the deflections for the beams, as you see here, for this load combination. For the others, you just need to select them. Options. Okay, so this will be the deflection for this load combination. You can check for number of studs that we need to place between the slab and the steel box girder. So I'm going to use this design mode. Okay, and let's say if you just double click on one of the members, this is the design results. You have all of the required parameters or design results here. So this is for bending and axial. For shear, you have it here. You have the design load rate, and you have the number of required studs here for positive or minus bending. For the deflection, we didn't define any deflection, so we don't have any results for that here. And you can check the design report for this member here. Okay. You can check the design results for construction stages here. For example, stage 1 is like this. Stage 2, which is the just concrete box girder with poured new concrete, and we don't have any composite action yet in stage 2. So because of that, some of the members you're seeing higher values. And stage 6 and 7, we have the composite action activated. So again, we have better ones. Okay, so the benefit of using finite element plates, after we check the design results here, we can always check for the stresses in the beams or slabs. So this is the benefit of using finite element plates that I'm going to show it right now. So I will unmask everything or hit D. Select these finite element plates. Okay, and mask them. So we will not see the linear members. And right now you can check for the stress results on these members. So let's say if you want to check the stress results on this load combination, select it. We go to view options, and here, as you see, we have a tab called finite element results. Here you activate the color counter, and here the type of results that you can get from a finite element plaque. For example, if you want to check this stress sigma max, select it and OK. And here ADA will show you the stresses in these finite element plates. You have the values here, and these are the color codes, and these stresses are all under this load combination. You can check for the other one, the minimums. And you can always select and separate the steel from concrete by selecting them by our window here. So here I just want to check the results for steel, so I will separate the steel plates, mask them, and here, as you see, I have just the steel results, stresses. You can view other bendings, shears, all of the results here, axial force, infinite elements. You can always view all of them here. You have the top and bottom layers, also results for top and bottom layers. And also you can just select the concrete. So to do that, again, we need to select all of the finite element plates, mask them. So right now you have all of the finite element plates, and now we can separate this time the concrete part. So window, select the concrete, mask it, and right now you have just results for the concrete slab. For this load combination, and the results is for sigma maximum. You can check for minimum also. So as you see, close to the supports, we have some extra forces here. Okay. And also you can check out these numbers or results numerically. So for example, if you want to check this here, you need to just double click and you will have the results numerically here, so you can check them out or copy and paste them to Excel. Also, you can define a better view or better color counter here for finite elements. So if you click this icon here, as you see, ADA right now just uses 9 colors. You can change it to up to 1,000. So let's say if we go with 225, as you see, you are much more finer color codes. Okay, select the plates and mask them. So as you see, the results are more finer here. The other opportunity or feature that you have here is to check the deflection for the finite elements. So you can go to view options, and just select this here, and deflection can be here. Okay, I'm going to diminish it. And for example, let's say if you want to check the deflection in stage 1 for steel plates, you have it here. And if I add the scale or increase the scale, you will see it here. And you can always double click to have the results. Okay. For example, you have the deflections here. You need to always uncheck this here. Okay. And this one will be none. Okay, because we are checking just for the deflection. Also, you can check out for the reactions from supports. So you can select this here, select supports, Control H, and these are the reactions from the support, Rx, Ry, and Rz. Under this load combination, stage 1, and to check these the reaction in supports visually, you can use this part here in this view options window. So if you want to just check for Ry in the supports, okay, you can use that option and you will have these reactions here. You can change the design load combination here. Okay, this was a brief example on how to model and design a steel box girder bridge. It was a 3D model. So we also learned how to check the results for finite element plates. If you have any questions, just let us know in our email here. And thank you very much.